Let's conduct a flexural analysis of a beam. In this problem, we have two parts of the problem. We have one system of a W24 by 84 at 8992 steel, one at 12 foot, and one at 25 foot. And we're going to analyze both of them for flexural strength and see whether they can support the loads that are given to us here. We are going to be doing this using LRFD. We're just doing this for purposes of simplification. ASD is an extremely similar process all the way up to the end pretty much. Just want to simplify it and cut as much time out of this video and help you guys get through this problem. So, a couple of parameters that we're going to need for this problem. We have a live load of 780 pounds, a dead load of 300 pounds. As I said, we have two lengths, and we'll see why when I get further on in the problem. We're going to analyze different types of lateral torsional buckling with this problem. We have a simply supported beam with supports only at both ends. As I said, A992 steel, W24 by 84, and the lateral support comes only from the end, and that is important because if you have a problem where we'll get right into it. So what are the things that we really need to get into this problem? So first thing we're going to do is we're going to analyze whether the shape is compact. This isn't too difficult to do. We can use our equations for lambda P and lambda R, which we'll go over in a minute. Number two, I have written out here that we need to analyze the web for being compact. But what do we know about shapes in the manual, at least I shapes in the manual? They are all compact. So this step is already done for us. We actually don't need to check this. We can assume that the web is compact for the shape. Next, we need to analyze the LB, the LP, and the LR values of the beam. So those are going to come from the lengths that we're given. Well, LB comes from the lengths that we're given and the parameters that we have. And then LP and LR can be determined from a couple of equations that we'll get into. But essentially, if LB is less than or equal to LP, we do not really deal with lateral torsional buckling. And the nominal moment strength can be considered equal to the plastic moment strength. If you have an unbraced length that is between parameters LP and LR, your beam is subject to inelastic lateral torsional buckling, and we're going to be using this equation here, which is in fact, that is AISC F2-2. Just keep writing these down so that you guys have records for them if you want to go look them up. This is F2-1 right here. And for LB is less than, or LB is greater than LR, you're subject to elastic lateral torsional buckling. And that will be the case B that we end up going through. And this comes from F2-3, and then we need to find FCR, which we can get from equation F2-4. So we can start getting into this problem. A couple of very simple things. We'll just go through part one real quick. We'll analyze whether the shape is compact. If you're familiar with the AISC manual, you can look at it and you'll see that the designation in table 1-1 has the designation C, which means it is slender for compression, but we don't see F, which means it is non-compact for flexure. But we're still going to analyze it just to make sure you guys know what we're talking about. Lambda is equal to BF over 2TF in the manual. If we pull that value out, we have, what is that? That is 5.86. You'll start to remember the values for lambda P and lambda R eventually for A992 steel, where we have Fy equals 50, E is equal to 29,000 for all structural grades of steel. So you're going to get the same thing every time. This equation is 0.38 root E over Fy, which is 9.15, and lambda R is 1.0 root E over Fy, which is 24.08. So, with that being said, lambda is less than lambda P, and that is less than lambda R. So, flange is compact. Yay, that knocks something out. So what that means essentially is that our member is not subject to flange local buckling, which means that the two things that we have to analyze really are, really the only thing we have to analyze is lateral torsional buckling. or technically speaking yielding, but that's just looking at MP. That would be flexural yielding. So flange is compact. 2, we know the web is compact. And then that means we can move right on to our analysis of LB. So we're going to start now. This is where we're going to split up into parts A and B. We're going to proceed with part A right now, and we'll go onto a new page to do that. Part A, I'll write it this way, 3A. We are told that our beam was 12 feet long, and since it is only supported at the ends, that means that LB is equal to 12 feet. So we can calculate LP and LR right here, and that's going to be the same for the beam no matter where you're looking. These equations are kind of miserable, so I'm going to write them out, and then I will tell you where to get the value out of the book. This is the value for LR, or pardon me, this is LP. Goodness me, LR, and this is AISC F2-5. And these are all, when I write these, I'm writing equations down. If it's a table, I'll normally write the table. But when I say AISC F2-5, I mean equation F2-5. And then LR is this really, really, really ugly equation that I will write out, and then I will tell you where to get it from in the table, because there is a table that you can use to get this. So it's 1.95 RTS times E over 0.7 FY. And then we go into this massive square root, and you'll see very quickly why I prefer using the table for this. There's really no need to do this. This is all tabulated already, so it doesn't make a lot of sense to be doing this by hand. It doesn't make any sense to be doing this by hand. And if you read into the literature a little bit more, I'm pretty sure you can find information on where this 0.7 FY comes from, but essentially it has to do with the limit states that we're talking about. And as I was saying, I'll tell you the equation. This is equation F2-6, but if we look in table 1-1, what I'm going to suggest you do is you find your ZX, and ZX is equal to 224. And then what we're going to do is we're going to go to table 3-2 in the manual, and this gives us W-shaped selection by ZX, and we can find 224. You will find your values for LP and LR here. So LP ends up being 6.89 feet, and LR is equal to 20.3 feet. So with that information, we now know what equation we need to proceed with. So if we come back up here, we have a 12-foot member here, so we're going to be subject to this case right here, which is inelastic lateral torsional buckling. And this is where this fun case comes up. And I'm just realizing, oh, I don't have this written as a step. Okay, well, this introduces the problem of CB, which we can talk about right now. So CB is a very important value, and it accounts for non-uniform bending. There's tables for it. The one that I would normally, the one that's generally referred to is table 3-1, and you will see that for this type of loading scenario, CB is equal to 1.14. So this allows us to kind of increase the nominal moment strength of it. You'll see from the equation that we have up here, which I will copy and paste down here because I don't feel like rewriting it all again. It's a multiplier that increases the nominal moment strength. So when we use that, we are actually increasing this nominal moment strength past what we would otherwise have. So this equation looks scarier than it is. But one important thing to remember about this is that this value, then the nominal moment can never be larger than the plastic moment. That's just a fact of this, that it can never be higher. So we can find MP from the table, from table 6-1, if we want to, and look at an unbraced length of 0. But I don't personally like doing that most of the time, just because the calculation for MP takes about 2 seconds. MP is equal to Fy ZX, because we're looking at strong axis bending, and that's literally all there is to it. So with that information, oh, I should have also mentioned, this is equation, equation F2-2. So with this information, we can kind of start to plug things in and see what we get. So Mn is going to be equal to 1.14 times Fy times Zx, right? So now what we can do is say, well, actually, let's break this apart first a little bit more. CB Fy Zx minus quantity Fy Zx minus 0.7 Fy Sx times LB minus LP divided by the quantity LR minus LP. And if you have done anything with flange local buckling, this probably looks pretty familiar, and it should, so that's a good thing. Basically, if you're dealing with flange local buckling, these are just replaced with the lambda values, and then that's the majority of what changes in the problem. Very similar format. So we can go through and start plugging stuff in now. But let's be keeping good track of our units while we're doing this, because CB is unitless, but FYZX is going to give us something in kip inches. So we're going to convert that, because this here is in feet, right? And we don't want to get all of this confused. So we will go through and divide stuff by 12 as we go. So this is going to be 50 times 144, which we found, or pardon me, that is 224. Wow. And then we'll divide this by 12. Subtract basically the same thing. Not basically, exactly the same thing. Minus 0.7 times 50 times Sx, which for a 2484 is 196. And that's all dimensional data, so you can get, well, Fy is not, but you can get that data from table 1-1. And then we can do LB minus LP based off of the values that we were given from table 3-2. So 12 minus 6.89. And then we will have 20.3 minus 6.89. And from here, this is just plug it into your calculator and solve. And we can do that right now. So go through again, start putting this into your calculator, make sure you're tracking. 50 times 224 divided by 12. And this is where parentheses can really start to mess with your calculations. So be very vigilant that you're keeping good track of them, that you're properly properly getting all of them in the right place, because I've had many a problem that was messed up by exactly that. And I would hate that to be the reason you lose points on a test or anything like that. So I get 248.336. It has to be less than or equal to 50 times 200. Oh, this is supposed to be 224. 224 divided by 12 is 933. So what we can do, if these numbers seem a little bit suspicious to us, is we can go to table 6-1 and calculate or look at what the strength of the member is at that length and see whether these numbers check out. So the numbers that I'm seeing right now don't really check out for a member of 12 feet, so this is why I'm going to go back now and I'm going to check my calculations. So CB is 1.14. If anything, that should have raised this value, and it didn't by that much. Note that all the all the values in the steel manual in tables 6-1 and such like that are in fact already adjusted to be like calculated for lateral torsional buckling. So that's important to remember. And now I'm double checking to make sure I didn't miss a parentheses in here. It's looking like I might have. And yep, I think I did. Minus 0.7 times 50 times 196 divided by 12 times 12. I'll add another one here. 12 divided by, see, I'm pretty good at this stuff and I still just messed that up, so be very cautious about that. Minus 6.89 795.51, that seems more accurate. And times that 1.14, I have 906.889. See, now that answer seems more realistic. When you do enough of these problems, you will start to catch on to when a number doesn't seem quite right. So once again, I'll go back and I'll check table 6-1, see what I have. Table 6-1, at a length of 12 feet, I am registering 716 kips, which is interesting. There it is. I figured out what it was. Essentially, what happened is in the table. I always forget this. The tables give values for phi b, MNX, and phi b is equal to 0.9. Table was reading 716, right? But I was getting 795 without the 1.14. I hadn't multiplied that in. And if you multiply this 0.9 times 795, you get 715.5 roughly. Or 7, yeah, around there. So that's what was happening with that. Common mistake that I wanted to share with you and not hide, because that is a good thing to avoid and a thing that can hang you up pretty bad. So essentially, back to this. This equation checks out. This passes. So Mn is going to be, I should also clarify, this is Mnx because we're talking about strong axis bending here, is going to be equal to 906.889. With that, phi b is equal to, what would this be? Phi b is 0.9, as I just mentioned. Actually, I don't know what I'm talking about. So 0.9 times this 906.889. We have phi b MNX, which is our design strength, is 816.2 kip feet. Okay? So now we're done with part A for the most part. But what we still have to do is analyze and break down these loads. So to do that, I'm just going to do it right here. Case 2 is going to govern 1.2 dead plus 1.6 live. And we're going to convert these into kip feet instead of pounds per, or kips per linear foot instead of pounds per linear foot. So we're going to do 0.78 plus 300, well, actually, this is applied load, so what it actually is, man, I'm really getting these backwards right now. Remember that we have 300 pounds per linear foot of dead load. However, this is an 84-pound beam, so actually we have 0.384, because it's going to be 300 plus 84. And then this will be 0.78. And this is going to come out in kip feet. This will give us P, or WU, I should say. That will give us 1.2 times 0.384 plus 1.6 times 0.78. That gives us 1.7088 kips. And we know that for a beam with uniform distributed load, our M max is going to be equal to WL squared over 8. So we now come down and bring that information. M max is equal to WL squared over 8. Do a sanity check on our units there. That is kips per foot times feet squared. So kip feet, or foot kips, however you want to call it. 1.7088 times 12 squared divided by 8. And as you can probably guess from looking at this, this is going to pass by a large margin. Yes, our maximum moment is going to be equal to mu, which is the sum of our factored loads, is 30.758 kip feet. And with 816 feet, or 816.2 kip feet of capacity, we are well under where we need to be, which isn't too surprising, and it's good. Well, it's not good if you're the engineer who designed this building, because you shouldn't have picked the 2484, but I digress. All right, so now let's move on to part B. And part B has LB equals 25 feet. Well, we've already done the whole rigmarole, so we know LB is greater than LR, which means we have elastic LTB that we're dealing with. And quite frankly, this is not super fun, because we have to do MN is equal to FCR SX, once again less than or equal to MP. And this has, this is from equation F2-3. But FCR is really not a pretty equation. I'm not going to sugarcoat it. So this is from F2-4. And we have this gigantic mess. So it's going to be equal to CB pi squared E divided by LB over RTS quantity squared times square root of 1 plus 0.078 JCSX H0 LB or RTS squared. And all these scary numbers that you're seeing in here, or these scary variables you're seeing, RTS, J, C, SX, actually C, you have to know, C is just going to be is symmetrical, or is 1.0 for doubly symmetrical I shapes. That's F2-8A. But RTS and all of these things, you can calculate a lot of them out, but you're not going to want to. They're values that come from the steel manual in table 1-1. So that's going to be your best friend here. So let's just go through. We're going to start calculating it out and see where it gets us. So we have 1.14 pi squared, 29,000. And then do your sanity check on units, LB and RTS. RTS is going to be in inches. So we're going to take LB and multiply by 12, 25 times 12, divided by RTS for this is 2.37. Then we can go into our square root. 1 plus 0.078. J is 3.7. C is 1.0, so I'm not even going to bother writing that. SX we used before, it's 196. H0 is 23.3. Then we have LB over RTS again, so 25 times 12. And RTS is the same thing it was before, so 2.37. So go through here, 1.14 times, goodness, I already messed it up in my calculator. Pi squared times 29,000 divided by this quantity, 25 times 12 divided by 2.37 quantity squared, times this gigantic square root, 1 plus 0.078 times 3.7 divided by the quantity, 196 times 23.3, and then we have 25 times 12 divided by 2.37 squared again, and we have 28.889, which can check your units here if you really want. Unitless, unitless, KSI. These units cancel, so that's unitless. Everything in these parameters, so we have, this is inches to the fourth divided by inches to the third times inches, so inches fourth over inches fourth, and then this is the same, this right here is the same term as what we had here, so those are canceling again. So KSI is what's left, and that makes sense, that's a reasonable FCR value. So with that, MN equals FCRSX equals what we just found, so 28.889 times 196. That is our SX value, and then we're going to divide by 12. And we get 471.85. Now, this value we already have established is less than or equal to MP, because MP hasn't changed, right? That's a characteristic of the beam. That's Fy times Zx, and that was 933. So we're not worried about that. That checks out. MNX is 471.85 for, that's 5 technically, and then this is kip feet. So Phoebe MNX, which is what we would find in the design manual, should be 0.9 times this 471.855, and we get 424. Now, there's an interesting characteristic about this in that the value in the table is going to have 1.14. So if we want to check it against the value in the table, we're going to take this and we're going to divide out the CB, because CB is not accounted for. So that gives us, it should be Phoebe MNX at 25 feet should equal 372.52. We'll go check this at an unbraced length of 25 feet. And we see that it's between 396 and 351. And if we just average those out real quick, because we're at exactly halfway between those. The table only provides increments of 2 feet for this. We have 373.5 is what it's saying if you interpolate it exactly. But yeah, that answer completely checks out. That could have been a rounding error somewhere along the way. So yeah, that's how you go about this problem. So we've gone through this problem. We figured out how to do lambda calculations. We did CB. We didn't calculate CB out by hand, but for this type of problem, there's really no need to. If you really felt like it, you can do the equation for it. It is, let's see. I'll actually cover this at a separate time. This isn't really the ideal video for it, because for a uniform beam, you're always just going to know CB is going to equal to 1.14 for this case if there's only one support. So with that information, I hope you guys really found this video helpful. It takes a good bit of time to put these together, so if you could drop a like or subscribe, it'd be really appreciated. And thank you guys.